So what do we mean by logic?
And, not, or.
Yeah, right. So we can do what we call if this and this is true, if this or this is true. If this and this is true, then the output would be true. If this and this, if this or this is true, then the output would be true. If this and this is true, then the output would be false. Right? So that's the kind of what we're talking about logic. We started doing logic a long time ago with devices called, are y'all okay with relays? You understand what a relay is? Are y'all okay? So what is a relay? A relay is an electrically controlled switch. It does it by magnetics. So it's that wall thing. You know what that switch back there on the wall does? What does that switch do? Yeah, but it turns on that whole row of lights, right? So a relay is an electrically controlled switch. So you don't have to flip the light switch, right? You understand that? We could do it electrically. Now, of course, it uses magnetics. It has a device we call a solenoid in it. And y'all seen solenoids all the time, but you just don't know what they are. But I know now on what we did before is that if I put current through a conductor, it generates a magnetic field. Y'all remember my electromagnet? Not a very efficient one, but it worked really nice, right? So I was able to do pick that up. Well, notice on this guy right here, I've got the wire. So this is actually what we call magnetic wire, which has a really thin insulation on it because you want to really couple the magnetic field. But what I have it wrapped around is a straw. So how is this thing going to work? Well, what I'm going to do is I'm going to come over here, and what did I do with my nail? Here it is. So I got a nail, right, which is made out of metal. I got my metal. I'm going to put that nail in the center. And then I'm going to come over here, and I'm going to put some electrical current on this thing. And what do y'all think's going to happen? Huh? Oh, I plugged my power supply. To plug in my PLC. So I have no idea what I'm doing. No. My camera runs off the computer. I might unplug my computer. That's okay. It's got a battery. Okay, now I got my power supply. I need 3 hands. You know, see what it does? It just does what? Well, it just pulls it up into the coil. When I let it go, where could we, that's a solenoid go. Where could we use solenoid there? So what does a solenoid do? It takes electrical energy and converts it into a linear motion. Your starter's got a solenoid on it, so that's what it does. It pushes the gear on your starter into the gear on the back of your engine. Anybody ever been buzzed in to a door before? What does that use? Solenoid. How does your washing machine turn water off and on? Solenoid. The thing drops down and stops the water up, pulls it back up, right? Y'all understand that? So we use solenoids all over the place. We use solenoids to position fluid power valves. How do we route the air when I want to make something extend or retract? Well, we use a solenoid to push a vein in there. It's just a valve. But instead of me going out there turning, right, it does what? We use solenoid to position things all the time. If I was to take a solenoid and put contacts on the end, you got a relay. That's all a relay is. A relay is nothing but a solenoid, but it uses that linear motion to do what? Open and closed contacts, right? That makes sense? So you can actually see the wire. Now, industrial solenoids are usually encapsulated, so you can replace them. Of course, these are AC. These are AC. So here's the solenoid right here. Here's the coil for the solenoid. In industrial, the coils are encapsulated because the wiring they use is so thin that you could have problems with it. So we could take this apart and we could replace the coils right there. So this is the solenoid down here. And then, of course, when it energizes, it pulls that thing into it. And then what does it do on the top? Yeah, it opens and closes switches. So this switch right here, it's in the open position. When the solenoid is energized, it closes it. This switch over here is in the closed position, right? And when the solenoid opens, it does what? By the way, when y'all leave my class, you're supposed to let me know. Okay, what's your name?
Right.
Okay, thank you. I did make that clear, right? It's on the syllabus too. Huh? You're supposed to. Guys, I don't need a reason why you got to leave. All I ask is you just let me know. So everybody see this, and we had quite a few people leave without telling me. So I'm gonna call roll again, and I can fuss at me. And I can understand y'all want to go, but if you already know this stuff, that's fine. But when you fail your test, then you know. Are we okay? So this is a relay. And we can do logic with this. We can do ands, we can do ors, we can do nands, we can do nors, we can do nots. So we can do all this logic. So relay logic has been around for years. Relays can't do math. So this is where the PLC comes into play. So everything that y'all do this semester to start off with, we could wire it with relays. All right. This is a controller. I'm going to learn the different characteristics. Huh? Not this PLC. Well, yeah, this PLC could control that. This PLC has AC outputs. It has relay outputs, but they're wired for AC, 120 volts AC. That's 120 volt coil on that. So yeah, this PLC could energize that relay. But what can we have what can the contacts be controlled? Higher voltage, but the coil can be AC, but the contacts could be controlling DC. So I could be using that to control DC. I could be using a higher voltage or a lower voltage, or I could be using the same voltage. So we'll look at that when we try to do logic. So that's a control relay. A control relay is not designed to handle heavy loads. It's in there for control. So it never gets into what we call the power circuit. So usually we divide our control circuit into two sections. We have the control circuit, and then we have the power circuit. Right? You understand? The control circuit, we want it to be low voltage. The power circuit is usually going to be what? High voltage. The control circuit controls the power circuit. Right? You understand that? But a relay whose contact stays in the control circuit, we call it a control relay. So a control relay, its contacts never control a high power device. We get into these big old relays that we'll look at, motor starters and contactors. Those are the guys that are to run power. So first of all, we need to understand a relay. To understand relay logic, we need to understand relays, right? Now what they've done is they gave us rules. So this is the symbols. We got to understand the symbols. So when we come up here, gotta go. I know your name. It's gonna take me a little while to get those names in. I know the class goes to 9:30. I just want to make sure. Use a symbol, so we're going to have to learn symbols, create logic diagrams, using standard relay logic rules. Place the comments on the relay logic. We're going to look at this, and we'll actually look at a real relay logic diagram. Okay. And then we'll compare that to PLC. The guy that wrote this, he didn't. Undoubtedly, he played with PLCs all his life and didn't get into actual relay logic. I've never heard them called elementary diagrams. All line diagrams, we use that a lot. Relay logic diagrams, the guys don't use that, they just call these ladder diagrams. And that's the name that you're going to hear used. And we'll call them ladder diagrams. I'll call them ladder or I'll call them line. I'll switch between those two a lot. And of course, the first normally what we do, in the old days, what we used to do is we used to take a relay logic diagram and control it to PLC. We don't do that much anymore. What we did is figure out what physical devices we're going to have to control. What can we do with our PLC, and then we come in and do that. But you still got to understand the symbols, because when you draw how you connect those input ports and those output ports, you're supposed to draw the electrical symbols, not the PLC symbols, the actual true control symbols. Does that make sense? And but they're saying you draw the relay logic diagram first, and then you convert it to PLCs. How many people do you think does that? But that's what we used to do. Used to controlling, when we had to program computers, we had programmers, and then but the programmer very seldom saw the computer. And what the programmer would do, he would develop a program. Used to load the code of a program in the computer, we put them on all these punch cards. I don't know, the old Social Security checks used to come on the punch card. And then they would send it to a key punch operator. The key punch operator would take your code, and then they would do what? They would punch the key. They would give it to the computer operator. The computer operator would run it through the computer, see if it compiled okay. If they got any compiling errors, they'd give it back to the program. So it was imperative that the program be right the first time, because you kept doing what? So we used to do flow charts. We put the program. We had these little symbols for everything we did. If it didn't work in the flow chart, it wouldn't do what? It wouldn't work on the program. So we started off with a flow chart. Then we did what? Then we wrote the program. Then we did what? Gave it to the keyboard. Well, we didn't know there was any problems. This is the problem, because most of the time the bugs didn't pop up, or the errors didn't poke up until you tried to compile it. So they would load in the computer, they would compile it. Then they would give you a list of the errors. Then they'd give that to the program. The program would do what? Debug it. They'd give the new code to the key punch operator. The key punch operator would punch the cards, and then they'd give it to the computer operator. So it was imperative that the program, that you didn't keep going through that cycle. So you wasn't a good programmer if it took you 5 months, because every time you compiled it, you had a new error and thing, right? And what do we do now? We may flow chart the program. But usually we get an idea. We can look and say, okay, I want a program that does this. And then we come up and we figure out what input devices we need, what output devices we need, and then we figure out the program. So, and then you do the compiling. So when you try to download your program into the PLC, if you got any errors, then odds are it's going to tell you got what we call syntax errors. You know what syntax is? What's syntax? Language, not the tax on cigarettes. Which are in the whiskey and stuff like that. Yeah, it's the correct way of writing in a language. So your compiler will only find syntax errors. It won't find programs that are written right? You understand that? I mean, written wrong. So if you wanted to use output 3 and you used output 5, a compiler's not going to find that as long as if you use the right syntax, right? So we still have problems with that. So they check the syntax when you try to compile it over. What RS Logic 500 does is it checks your syntax while you do it. So right off the bat, it gives you a syntax error because you start off with a blank run, right? You understand that? So what we do is we start off with what they call power rails in PLC, in PLCs and also in ladder diagram PLCs. And we generically, we start off like this. And this is where your power is at. This one on the left, we call that L1, and this one on the left is L2. This is considered to be the common of the circuit. Now, when you look at a PLC diagram, they might call it PCL1 and PCL2. They'll give it a different name, right? Understand that? But you should see that. And then what we do is we build our circuits between these two. So that's a symbol for a normally open push button. Line 2 is considered to be the neutral. But it's considered to be the return, but that's a relative term when you're dealing with AC. So AC, we usually call it a common or neutral. Now, there is a difference between a common and a neutral. Anybody that works in electrician, they've heard the term neutral, right? So what is neutral? If you look in the NEC code book, they never use the term neutral and they never use the term hot, right? Anybody ever looked at the NEC code book? Because it's so neutral. When we use it in electricity, if we use the term neutral, it is a grounded conductor. So that's what they call it. They call it the grounded current carrying conductor. That's what they call it in the code book. And what we call hot, what electricians call hot, they say that is the ungrounded current carrying conductor. So what is ground? Why do we run 3 wires? So if neutral is grounded, why do we have a ground? The ground is not supposed to carry current. So what we do is we take that ground and hook it up to all your metal surfaces. And if your ungrounded conductor comes in contact with the metal surface, it pops your breaker. So that way the chassis, these metal chassis will never become electrically have power on. So the neutral is a current carrying conductor, right? You understand? So we can't say this is a neutral. A common is just where we connect a bunch of things to. So we don't have to ground the conductor, but we got to have 2, right? We got to have one that is our reference, and then we got to have on DC we got to have a common. We're going to use either minus for L2 or we're going to use plus for L2. If I use minus for L2, then I got to use a plus for L1, right? If I use a plus for L2, then I got to use a minus for L1. And that's what syncing and sourcing is you just change your commons around. So we build these circuits between L1 and L2. And this would be my load, so I'm just going to call it a relay. It could be a light bulb, but we probably wouldn't put a light bulb in a circuit like this. Now, what we do is one of these circuits, we refer to this as a rung. Sorry. And the rungs run from between L1 and L2. Now, so you can see why I got the name ladder diagram, because it looks like a ladder. It's got the two outside. And you can see why we call them rungs, because these individual circuits looks like what? Rungs on a ladder. So we call them rungs. And this is where we start getting a little difference between what we call a PLC and a control system, or control diagram. And this guy right here, this is where he has problems. And some people call this a line diagram. The language we're going to program in is called ladder language. They don't call it line language; they call it ladder language. So the term we use most often is we call them rungs. And are we okay? So this makes kind of sense right now, right? So this would be. Now this guy is dealing with a PLC. This is relay logic. This is not PLC logic. We don't have limit switches inside of PLC. So this is a symbol for a limit switch. This is a symbol for an only open push button. This is the symbol for contact that's being controlled by a relay. But what we do is the relays, we give them names. So they're calling this what? CR1. I mean, they're calling this CR. So this is where the guys got it wrong. We wouldn't do this right here. We just call them CR. This is what we call a normally open contact. What does that mean? Well, if this thing is de-energized, we put no voltage across the coil, this contact right here would be open. So when we talk about normal, it's when the coil is not energized. Y'all understand that term? So the plunger is not pulled in. So this is a normally open contact. If I press that button and this limit switch is closed, the relay will close, this contact right here. Right? If I break the circuit, this will open, this right here. Everybody okay? This is a symbol of a solenoid. Y'all see the solenoid, right? All it is a guy that takes electrical energy and creates a linear motion. We don't see the rod or the armature that moves. All we see is the coil that controls that thing. Everybody okay? What he's doing here is he's using rung numbers. We do not, in motor controls, we do not list rung numbers. So in this is a big difference. In PLCs, they number the rungs. In motor controls, we number the line. Now, a line is anything that moves like this, right? You understand that? So what we would do is, this is what we would do with motor controls. This right here would be line 1, this right here would be line 2, this right here would be line 3. So we don't number rungs. In PLCs, we number rungs. In motor controls, we number lines.
Still one load per rung?
No.
No? Multiple loads?
One load per line. See, so now I can come up here and I can start doing this. I can't do that because that would put two rungs in the same line, right? You understand that? But what I could do is I could come down here and put go around that, right? So I could come down here and do this. And I could put another load right there. So that's a symbol for a light bulb, a lamp. Now that's legal. So the rule is, We can have many loads per rung, but we can only have one load per line. That's the rule. This guy's got it all. He says that we can only have one load per rung. He's wrong. This will get the same number, by the way. So if the lines line up, this line don't get a number. So when you find a line, any line that lines up gets the same number. Everybody okay? Yes or no? Now what we do, and this guy's got it wrong too. So this is a line diagram, by the way, a ladder diagram. And I'll give y'all this. Here. This is actually a true line diagram or ladder diagram. So what we do is over here on the right hand side, we put the contacts that are controlled by that relay, their location. So I'd come over here on here and I would put out beside on the right hand side, I'd put 2, and then I'd put a comma and I'd put 3. So right off the bat, when I see this relay, I said, well, this guy's got a contact in line 2. I would come over here and do what? Follow line 2 over, and there it is right there. It says it's also got a contact in line 3. I would come here down here to line 3, and I'd start following that over, and there it is right there. These are called numerical cross-reference. These are called line numbers. These are called numerical cross-reference numbers. So what's the rule? What? Many loads per rung, one load per line. And this is also true on PLC. So we can hook loads in parallel, we just can't hook them in what? Series. So okay. So look at that thing. I mean, good gracious. So you can't hardly see it. And you can't see the numerical cross-reference numbers, but that's not the same trend. But over here on the left-hand side, what I want you to notice is that every horizontal line gets a what? A number. Why don't this guy have a number? Because it's in line with that right there. So that's what I do when I look for contact numbers, is I just follow the line over. So notice all the lines, every horizontal line has a what? A number. Now I got a 13 out here by itself. Well, see, this lines up with what? That guy right there, right? You'll see that. This is a class called Blueprint Reading, by the way. This came right out of their book. What you're looking at there, that is one of the lines out at U.S. Steel in the galvanizing line, which I heard they shut down. This is actually a print from U.S. Steel. This is not, but they follow the same one. Standards, right? You understand? This is out of a book. That's actually a true thing, right? Now this guy here goes over like hundreds of pages. So when they give their contact location, they give it, and then this guy does. They start off with a page number. So I think this is page number 123. This has a disconnect in the So see, they call theirs PCL1 and PLC2. These are relays. So I can come over here and look at this. Now, this is telling us, this is on this page. So this is page 137. And this is line 2. And it says I have, if they underline it, it means it's a normally closed contact. If they don't underline it, it means it's normally open. Do y'all understand those terms? Somebody says yes. So what do I mean by normal? A normally closed contact would be like that relay I passed around. When the relay has no power on it, that contact is closed. That's what it means. So underline means I'm looking for a normally closed contact. So we learned two symbols. And I can't draw on this, but I can draw it on what we. This is the symbol for a normally open contact. This is the symbol for a normally closed. Everybody okay? Now, this is the name of the relay. So every relay is given a name. So this relay is called 5B1DB. It says it has a contact in what? 137.02. I come over here on my line numbers, I find 137.02. That's not that guy. It don't have the same name, right? You see that? This is called 5BJ. We're looking for a contact that has the same name as the relay that's controlling it. I come across there, and there it is right there. That's the contact that is being controlled by that relay. So the first thing we're going to do is give a relay a name, right? You understand? Generically in this, they'll call them C, R, and M, but out in real life, you only have so many M's, you have so many CRs, so they're going to give it a name according to what they do. This is number 5 drival, number 1 dynamic braking relay. Now what they'll do is they'll throw comments over here. And I think the book says the comments have to go on the right, but they'll put comments all over the place. So it comes over here and tells us the name, what that relay is. It says it's what? Number 5 drival, number 1 dynamic braking contact. But instead of writing all that up, they give it a mnemonic or a small name. It also says that we have a normally closed contact in line 57. I don't think we have line 57. I think it's on this sheet. How far does our line go down? Huh? Yeah. So this guy goes over multiple sheets. Let's see if we can find a normally closed contact. Huh? Contacts can be anywhere. You use contacts where you need them. That would be saying, why is this light switch so far away from the light switches over there in the hall building? You put them where you need them, right? Understand what we're saying. Contacts, by the way, motor control, these circuits are not showing you how they're wired. They're showing you how they logically work. Right? You understand? So we put the contacts, we put the symbols for the contacts where we need them, right? You understand? These relays could be side to side, or they could be, in this relay house, they must have had 500 relays running this line. So they couldn't get it on one diagram, right, and make it small enough for us to see. These are actually D-size prints, the ones this is reduced down. These are big guys. So we could actually read them real easy. I was trying to find a normal.
Line 13.
But that,
Line 13.
yeah, but we're trying to find the reference to it.
So it's
But now you can talk. Now I can say what? Now I can say, okay, everybody look at line 137-11. And all you do is what? Go over to the left, find that, right? You understand? Everybody okay?
Yeah.
So now we can talk about this thing instead of, okay, everybody go to the 3rd line from the bottom or the 5th line from the top. I can give you a line number. Okay? Y'all okay? And you can see this goes over multiple lines. And this is the industry standard, guys. This is the way we do motor controls. So what are these called? These are called line numbers. This is a normally open contact, right? This is the one, normally closed. Everybody understand normally open, normally closed? And that's the way we abbreviate them. We call that an NO, or what? Not no, normally open. We call this an NC, normally closed. Everybody okay? And this is motor control. And this is a symbol for what? A relay coil. And these are the contacts that that relay club. You can see some of these relays control a lot of contacts. Didn't I pass that one around that's got all those contacts on it? Huh? I think that was the first one I passed around. This guy right here. So this is one relay, and it's controlling 1, 2, 3, 4, 5, 6, 7, 8 contacts. It's one relay. This was normally open, this was normally open, this was normally closed, this one's gone. This was normally open, this was normally open, this was normally open, this was normally open. Somebody, the operator is off. So this actually has, so we can have relays with controlling a lot of contacts, right? So what y'all want you to do is the book, and I'll put the review for the test. It'll probably be Friday before I can get it up, but y'all have it for next week. What we do in this class, if you look at the Blackboard side over the left-hand side, one of the buttons says test. I don't answer questions on the test on the day of the test. So if you've got any questions on there you need to ask, then you need to email me, right? I'm gonna, as everybody did their, I've already graded, so I know you, the syllabus agreement, that was supposed to be done way before, right? Everybody's been on Blackboard, y'all did the syllabus quiz and all that kind of stuff that was required before last week. If you didn't, you probably got a 0 in it by now. The syllabus agreement is required by the courts, right? You understand that? Also, if you do the syllabus quiz, it's going to ask you, can I send you a remind? So what I'll do on this text, just to let you see the number that's going to pop up, it's a strange number. I'm going to say, this is Rich. And then you can reply to that. And then from then on, what can we do? Instead of using email, we can do what? We can text it. So that's a really good application because you don't have to have my phone number. And I can disable you if We had a guy doing our MSSC test. We was doing the MSSC, and it says down there, if you find any problems with the test, we need to report them. And this guy had worked in the field. He was finding questions all over the place. And he was sending all this emails, and they disabled his account.
They're like, fine.
Well, they thought he was a spam because he'd get so many emails from him so fast that they thought he was spam, so they disabled his account. So he couldn't do the MSSC certification before they did his thing. Okay, guys, see y'all Wednesday. Y'all have a good holiday.
Are you going to put your grade card?
Yes, I'll. I don't think my grade card charge goes up to that part. Let me see the number. That's 8.9. My code don't work.
That's one more chapter.
And that one, I just put a question mark next to it. Because it's not even 1,000, it's higher than 1,000.
They just want this.
Unless I did the binary wrong.
Yeah, I'm gonna have to look at that. None of these go up that high. He's got this bottom one is a huge number. That looks like it's. You know.
Well, I know the 1B4C is 6,988, and the BC is probably less than that.
Yeah, but even my count, I think I go up to,
Where do you?
I don't know, near as far as this. But I can't.
Oh, another question. Do you normally, when people leave early, do you normally mark them absent?
I'm walking hard.
They're just marking party? Okay, you marked me absent.
Well, you must have,
No, I was here. It was basically last class meeting on Monday. I left at 8. And
yeah, but you probably wasn't here when I called up.
I was here. I sent you an email and you never replied back to it.
You sick, man.
I did send you an email unless that link doesn't work. There's the email instructor on Blackboard.
No, it should work.
People on there.
Normally what I do is, our second assignment is to do what?
Email to teacher.
Yeah.
Yeah.
So I usually assume the first of the semester when I get emails is for that thing right there. So it's probably.
Yeah, I clicked that link that was on the.
We'll see. Yeah, it'll be in the folder.
You know what it's missing? It's missing a 3. Yeah, you said it might be missing a 1, it's missing a 3. It's 3,023, and answer says 0.
So what's your name?
Jeffrey.
It don't look like any emails are coming in here.
Uh-oh.
Uh-huh.
That's 112. That's January.
Well, this was last class. This is the last time I taught the class.
But yeah, but you basically had me mark it absent on the.
That's okay. I can take it.
Well, I've showed up on it. I just left that early.
Wait a minute. I need to figure out what's going on.
Yeah, that number is 3,023 instead of 1.
What's your last name?
KAO.
Oh, okay. I need to check that out. See, there's that. So that's sorted according to alphabetical order right there. And the first one is,
So something could be going wrong.
well, I need to see if it went into junk mail, but
You're still recording, by